Good day everyone. So I am assigned to report the line integral of vector field. Line integral of vector field, the amount of work that a force field does on a particle as it moves along as a curve. So as you see the picture, the blue represent the force along the C curve, along the curve. That is the curve. Line integrals of vector fields. In the previous two sections, we looked at the line integrals of functions. In this section, we are going to evaluate line integrals of vector fields. We'll start with the vector field. F xyj is equal to P of xyj I hat plus j plus q, q of xyj j hat plus r of xyj k hat, and the three-dimensional smooth curve given by r of t is equal to x of t I hat plus y of t j hat plus z of t k hat, where a is greater than or equal to t, greater than or equal to b. So the line integral of f along c is equal to the integral of f dot dr along c is equal to the integral of f of r of t dot r prime of t dt along a and b. Note that the notation in the integral of the left side, that really is a dot product of the vector field, and the differential really is a vector. Also, f of r of t is a shorthand for f of r of t is equal to f of x of t, y of t, g of t. You can also write line integrals of vector fields as a line integral with respect to arc length as follows. So this is the face of the arc length. So the integral of f dot dr along c is equal to the integral of f dot t ds along c, where vector t of t is the unit tangent vector and is given by the vector t of t is equal to r prime of t over the magnitude of r prime of t. If you use our knowledge on how to compute line integrals with respect to arc length, we can see that the second form is equivalent to the first form given above. So the integral of f dot dr along c is equal to the integral of f dot vector t ds, and it is equal to the integral of f of r of t dot r prime of t over the magnitude of r prime of t, the magnitude of r prime of t dt. So it is equal to the integral of f of r of t dot r prime of t dt along a and b. In general, we use the first form to compute this line integral, as it is usually much easier to use. Let's take a look at a couple of examples. So we have example 1. Evaluate the integral of f dot dr along c, where f of xyg is equal to 8 x squared yg I hat plus 5g z j hat minus 4xy k hat, and c is the curve given by r of t is equal to t I hat plus t squared j hat plus t cubed k hat, which 0 is equal or greater than to t, greater than or equal to 1. First, we need to the vector field evaluated along the curve. We have f of r of t is equal to 8t squared of t squared t cubed I hat plus 5t cubed j hat minus 4t of t squared k hat. So it is equal to 8 to the t of 7 I hat plus 5t cubed j hat minus 4t cubed k hat. Next, we need the derivative of the parameterization. We have r prime of t is equal to I hat plus 2tj j hat plus 3t k hat. Finally, let's get the dot product taken care of. F of r of t dot r prime of t is equal to 8t to the 7 plus 10t to the 4th minus 12t to the 5th. The line integral is then the integral of f dot dr along c is equal to the integral of 8t to the 7 plus 10t to the 4th minus 12t to the 5th dt, and it is equal to t squared t to the 8th plus 2t to the 5th minus 2t to the 6th evaluated to 1 and 0. So the answer is 1. We have the example 2. Evaluate the integral of f dot dr along c where f of xyg is equal to xg I hat minus yg k hat, and c is the line segment from negative 1, 2, and 0 to 3, 0, 1. Well, first we need the parameterization of the line segment. So we saw how to get the parameterization of the line segment in the first section on line integrals. We've been using the two-dimensional version of this over the last couple of sections. Here is the parameterization for the line. We have r of t is equal to 1 minus t, negative 1, 2, 0 plus t, 3, 0, 1. This is equal to 4t minus 1, 2 minus t, 2t, and t, where 0 is greater than or equal to t and greater than or equal to 1. So let's get the vector field evaluated along the curve. You have f of r of t is equal to 4t plus 1 t I hat minus 2 minus 2t of t k hat. That is equal to 4t squared minus t I hat minus 2t minus 2 squared k hat. Now we need the derivative of the parameterization. We have r prime of t is equal to 4 minus 2 and 1. The line integral becomes the integral of f dot dr along c is equal to the integral of 18 squared minus 60 dt approaches 0 to 1. So it is equal to 6t cubed minus 3t squared evaluated to 1 and 0. So the answer is negative 3. So let's close the section out by doing one of this in general to get a nice relationship between line integrals of vector fields and line integrals with respect to x, y, and z. Given the vector field f of x, y, z is equal to p I hat plus q g hat plus r t hat, and the curve C parameterized by r of t is equal to x of t I hat plus y of t j hat plus g of t k hat, where a is greater than or equal to t, greater than or equal to b. So the line integral is the integral of f dot dr along c is equal to the integral of p I hat plus g q j hat plus r k hat dot x prime I hat plus y prime j hat plus j hat z hat k hat, z prime k hat rather, dt. So it is equal to the integral of p x prime plus q y prime plus r g prime dt along a and b. It is equal to the integral of p x prime dt along a b plus integral of q y prime dt along a b plus integral of r g prime dt along a b. It is equal to the integral of p dx along c plus the integral of q dy along c plus the integral of r dj along c. It is equal to the integral of p dx plus q dy plus r dj z along c. So we say that the integral of f dot dr along c is equal to the integral of p dx plus q dy plus r dj. Note that this gives us another method for evaluating line integrals of vector fields. This also allows us to say that the following about reversing the direction of the path with line integrals of vector fields. Fact that the integral of f dot dr along negative c is equal to the negative integral of f dr along c. This should make some sense given that we know that this is true for line integrals with respect to x, y, n, or g, z. And that line integrals of vector fields can be defined in terms of line integrals with respect to x, y, and g. So the difference between line integrals of scalar and vector fields is that the scalar line integrals are integrals of a scalar function over a curve, which measure the area under the curve. The vector line integrals are integrals of vector field over a curve, which measure the work done with the field along the curve. The scalar line integral depends only on the magnitude of the function and the curve, while the vector line integrals depend also on the direction of the field, the curve. So that's all. Thank you for listening. Good day, Merry Christmas, and God bless.